All right, folks, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 360 Control System class. And today is actually lecture 6. And first of all, can you guys hear me well? And also watching my share screen under the doc cam? Any trouble of them? Any feedback? You guys hear me?
Hello.
All right. Thank you, Adam. Thank you, Noah. Thank you, Alex. All right. If so, then let's proceed. Okay. Recalling the last week, what we have done is the block diagram reduction, and by reduction, it means how to organize the given complicated multiple block diagrams into one single block representing the total transfer function of the system. So how to do that? Now we first of all learn 3 basic block diagram configuration, right? What are those 3? Anyone remember? 3 basic ones. They're very important, okay? They're easy, but they're very important. We will see why, okay? But first of all, who are they? Anyone remember?
Is cascade, parallel, and feedback.
Excellent. Molly was right. Okay, so cascade, parallel, and feedback. Okay, 3 basic configurations. Okay, we will see why they're so important. Okay, and the next we learned a little bit the block diagram algebra. Now, what does it mean? The block diagram algebra is used to move the blocks. Okay, is to move the block. How to move the block? This is the algorithm. How to move the block and what is the consequence, and how to make the after move, post move block diagram equivalent to the prior block diagram. Okay, this is the algebra we're going to learn how to move the block and why we move the block around. This is also very, very important question here. Why we are doing the moving? Okay? Why we are doing the moving? Very, very important question. After moving, we want to find or say somehow combine those 3 basic block diagrams. Okay, we want to somehow come up with one of those 3 basic ones. Okay, cascade, parallel, and feedback. Okay, this is our goal of moving the block. Now keep this going in your mind, because which block to move and where it is going, all up to this goal. The goal is, once again, to come up with one of those 3 basic diagrams. Okay, keep this in mind. We will see how to really apply them in the examples. All right. So now the algebra, or say the algorithm, okay, moving algorithm. We have 4, only 4. From here, you can easily tell the first 2 are actually what? The past a summing junction, right? What matters is you pass the summing junction from the input to output, or the other way around. Same pattern to this 3rd and 4th. This is past a peak-off point, okay, rather than the summing junction anymore, right? Now also 2 ways. One is from input to output. Another is the from output to input. Okay, so 2 by 2, 4, up to 4 algorithms. Okay. Now let's talk about the details about them. Okay, let's talk about the details about them. Okay. All right, first one. First, let's just talk about the past as a summing junction. As we just mentioned, we have 2 ways to pass it from what? First one, let's talk about from the output. Okay, from output to input. Here, once again, this is what? Moving one block from output to the input of a summing junction. Okay, be clear on this complete statement. Okay, you need to be very clear. We are moving one block, one and one only. And also it is a block. We are not moving summing junction, okay? Be very careful. We are not moving summing junction. We are moving a block, passing the summing junction, okay? Then what is the algorithm? Algorithm is saying after moving, okay? Go ahead, you can move. And then after moving, you need to do something. Okay? After moving, other inputs of this past summing junction need to do something. Need to do what? Need to be multiplied by the moved block transfer function. Okay, this is the statement. Let's see what I'm really talking about. Okay. Well, let's assuming we have a, of course, this is a portion of the complete block diagram, but it's enough for us to understand the algorithm. So we are assuming we have input signal R going into a summing junction, and we have another input because summing junction, generally speaking, receiving more than one input, right? So this is the X second input to the summing junction. Now output of the summing junction is feeding this block with transfer function of G, capital G. And then we have output from there, which is C. Okay. If this is clear, then what you want to do is, let's assume we are trying to move this block G. Because this is the output side of the summing junction. This is the input side. So we are moving this G from the output side to the input side. Which is input side? Obviously here, right? We're doing this moving. Assuming we are doing this moving. And then what is the resultant? Of course, must be equivalent. Okay, this is the key. Well, you can't do whatever you want and then end up with a inequivalent resultant block diagram. That's making no sense, right? So the resultant block diagram must be equivalent. And according to the algorithm here, what does it look like then? First of all, after moving, what does it mean by after moving? So your R remains here. However, your G is now here, right? Summing junction. And then you have a C here. Does it make sense? This is called after moving. You're moving the G from output side to the input side. Okay, it happened. Just happened. However, the key is the other inputs of the summing junction, which is what? X need to be multiplied by the moved transfer function, moved block transfer function. The moved block transfer function is whom? In this particular example is nothing but G. So this other input X needs to multiply by G. What does it mean? We need to place a G here in the pathway of the X before entering the summing junction. Does it make sense? Of course, this plus minus sign remains same. Okay, you can't touch this. Now take a look at the left-hand side and the right-hand side, they're equal. They're equivalent. And they're equivalent. The other input of the summing junction, which is X, need to multiply by the moved block, which is G. And here we go. And here we go. Take a look for like 5 seconds. Any questions? And of course here, how can we prove these two are equivalent? How can we prove they are equivalent? This is a very straightforward, right? So we just derive C for both. Let's see if both C are same, right? So first the C equals what? So R plus minus X, right? First of all, R plus minus X. And then equals to this signal, right? This signal times G equals to our C. This is for the first one. This is for the first one, original block diagram. The second, after moving one, let's see. Here, your R need to go through a G, right? And equals to this signal. This signal plus minus this signal. This signal equals what? Equals to X times G, right? And then the result is C as well. Look at 2C what? Exactly same, right? Exactly same, okay? 2C are exactly same. Any questions? Is this clear?
Yeah, actually, so if the end result equals to C, then the whole diagram equals the other diagram. Is that what you're saying?
Yes, two diagrams must be equivalent. This is after moving, you have to achieve this. You have to guarantee this. Otherwise, your moving is illegal, basically. Otherwise, your moving is illegal. You can't do that. All right, if this is fine, then we can move on to second one. Okay. The first move is from output to input of summing junction. Let's see the second move, which is the other way around, from input to the output of the summing junction. Here, the red color thing remain. Okay, the red color thing should remain. We're again moving one block with certain transfer function, and then from input to output of the summing junction. All right, so I just skipping them. Let's see. Here we need to see the statement of the algorithm. Algorithm saying, okay, you can go ahead to moving. Okay, but after moving, you need to do something. You need to do something, which is the other inputs of the summing junction. This time need to do what? Not multiply by, okay, but divided by. Divided by. So moved block transfer function. Right? This time it divide. It divide. Once again, we use the similar block diagram example to demonstrate why this is a valid algorithm. Okay, we have yes, the input side, and then we have G here, block input side. Input side block of the summing junction. And we have output C over here, R here. We have once again another input of the summing junction, like this, right? This time the block is in the input side of the summing junction. According to the algorithm, now we are moving this block over the summing junction to reach the output side. And then it is saying the input signal X this time need to divide it by. What does it mean by divided by? It means times 1 over. Does it make sense? It means nothing but times 1 over. Divided by G equivalent to times 1 over G. Same thing. But inside of this block here, transfer function just a 1 over G. That means X divided by G. Right? Does it make sense? And of course, once again, let's see both C. Let's see both C. Let's see both C. First, well, R times G equals this signal plus minus X equals to C. Does that make sense? To the second one, what do we have? R here plus minus X over G. And then equals to the signal here, right? And this signal needs to times G equals to C. And you see what? Both are same. These two are same. Same again. Right? So the algorithm number 2. If you're moving a block from the input to the output side of the summing junction, what you should do? What you should do? Okay. Basically, once again, if you want to move it, go ahead, move it, make it happen. Just remember to do something else. Okay? Do something else. Okay? After moving, okay, you need to do something else to the other inputs of the summing junction, or either multiply by or divide by the moved block transfer function. Okay. Any questions regarding these two algorithms?
So if you have multiple inputs, or once you move the block, you need to do that to all of the other inputs, right?
Exactly right.
Okay.
Let's do like this. This is one X, right? Say you have another X1, another X2. And then here we need to do what? Does it make sense?
Yeah.
Yep. Same thing to here. Same thing to here. So here, other means all of the other. Okay, a plural. All of the other. Exactly right. Okay, it's a very good point. Very good point from John. All of them. All of the others. All of the others. No matter how many. Good. Good. Very good point. All right. If this is all right, then similarly, let's study the moving past pickup point. Okay, pickup point. Also two ways, obviously. Also two ways. And this time we are moving from output to input. Once again, it means the same thing. Okay, we are moving one block from output to input of the pickup point. From output to input of the pickup point. The algorithm saying, okay, just make it happen. Move it, but after moving. Other, or say all other. This time is not input, but output of the pickup point need to be divided by, okay, divided by the moved block transfer function. Not inputs, but output of the pickup point. Not multiplied by, but divided by. Okay. To summing junction, we have the other inputs. To the pickup points, we are talking about the other outputs. Why is that? Very easy to remember. Okay, very easy to remember. The summing junction could have multiple inputs, only one output. Well, the pickup points might have multiple outputs, but only one input. Does it make sense? So when we talk about others, others could only be inputs for summing junction and could only be outputs for peak-off point. All right, let's have a example here to demonstrate. So first of all, we have our input reach a peak-off point. As I just said, it might have more than one output. Okay, generally it does. Generally speaking, it does. Okay, we have output ones the C1 through C3. And then obviously we have a block G here at the output side of the peak-off point. If we want to move this guy from this output end to the input end, which is here. Does it make sense? This is the input end of the peak-off point. This is the output. Right? This is the second and third output. G is along one of the output. And so move this guy to the input. And what do we should do? Go ahead, move. Go ahead, move. Of course, after moving the output, this branch, this particular output branch is gone because you moved G away. So the G here, gone. Okay, remember that. But the key is the rest of the other, all of the other outputs of the peak-off point need to be divided by how many other outputs? 2, right? Okay. This is what does the algorithm tell us. Okay. You move one block from output side to the input side of the peak-off point. The other, who are the other? These two are the other outputs of the peak-off points. Need to be divided by. Divided by means times 1 over, right? This is the algorithm. And we can do a little bit proof here. So from here, auto proof here. Let's see, so C1 equals to what? R times G. C2 equals to R. C3 equals to R. Does it make sense? 3 output. In this case, what? C1 equals to what? Because remember, R is here. R times G. C2 equals what? R times G times 1 over G, right? So is C3. C equivalent. Right? Does it make sense? Any questions? Not very difficult, right? Nope. Not very difficult until doing some examples. Okay, if you see. Then let's learn the very last one, the very last algorithm. As you know, is from the input to output of the peak-off point. Okay. Algorithm saying, go ahead to move. After moving the other outputs, you can guess, easily guess now. Need to be what? Multiply, right? Multiply by the moved block transfer function. Very easy to guess now. Very easy to guess. Other outputs, this time multiply by. Right? Here once again, let's demonstrate. So what we are talking about here. Signal R goes through G and then reach a peak-out point here. And then we have output C1 through C3. So G is obviously at the input side, the input end of the peak-out point. Let's say if you want to move it to one of the output, because you have more than one output, so you can only move to one of them. Be very careful, okay? Your goal is to move to one of them rather than all of them. Does it make sense? You're moving when you carry a box away to place it to somewhere. You can't make one box appear at more than one place, right? That's a magic. This is not magic. You're moving this guy to here or here or here, okay? Not and. Okay, let's say if we move here, the input and G gone. It comes to here. And then what do you need to do? The other outputs need to be multiplied by the G. Okay. So by the black and the red, different color coded, so you can tell the black one is really you moved the original G over here. The red two G's are indicating what? They are the other outputs multiplied by the transfer function G. Okay. So be very careful where you moved, because from here to here, you probably cannot tell. G is moved here, here, or here. You can't tell. However, when you do the moving, you need to be clear. Moving to one place and one single place. And deal with the other two outputs as multiplied by the moved block transfer function. And the justification is very easy too. Actually, from here you can tell C1 equals to what? R times G. C2, C3 are same. All of them equals to R times G. And here, C1 equals to R times G. C3 is the C2, same two, right? Same two. So this is once again justification of equivalence between these two, right? Before and after moving. It must be equivalent. Otherwise, your moving is invalid. Take a look to see any questions. All right, before we really conduct the examples, let me emphasize one last thing here. So basically, in your heart, you need to understand how to know which block to be moved and where to move. In your mind, in your heart, or say wherever, you need to ask yourself this question. Before the exam, the problem is not telling you how to organize, right? The problem is just give you a complicated block diagram, interconnected each other. Messy. You need to tell yourself, first of all, that before anything else, which block I gotta move and where to move. So how to answer this questions. Okay, that's the key. That's the key. Okay, that's the key before anything else. You have two principles or two tips, or say. Okay, remember, number one is before moving anything, before moving any block, you need to check, okay, or say read through the given complicated block diagram. Check if any available basic one. Once again, who are the basic ones? Cascade, parallel, and feedback. Okay. Before conducting any moving, you need to check if any available ones. Okay. Maybe portion of the diagram contains a clear, very simple cascade or parallel or feedback. You want to combine, you want to do combine over there to make multiple blocks there becomes one. Does it make sense? Okay, before moving anything, you just don't hurry. Look through the system. Okay, look through the given system. Maybe it's very nice. You can see some, or at least one, okay, available, clear basic configuration, and then do the combination. Right, do the combination there. And next, if nothing, or you have done the combination for all of them, you move on to the second tip. You need to move the block. How to move the block? You need to keep thinking this way. Okay. After moving the block, you must can combine some injunction or peak off point. So that you are seeing less of them. I don't know if this tip may make sense. But the reason the given complicated system block diagram is so messy, the reason is it is including too many sum injunctions and or the peak-off point. Okay, this is something you need to understand. Why it's so messy? Many blocks. Well, is not necessarily introducing a complicated system. Okay, the interconnection will. Who is responsible of those complicated interconnection? The sum injunction and the peak-off point. So if you are able to reduce the number of them, of course, the system naturally becomes much easier. Okay? So after moving the block, you should be able to see what you can easily combine multiple sum injunction or peak-off point. Okay? You need to combine them. For example, I can give you a simple example. You have sum injunction here. You have block here, sum injunction here, another block here, and then sum injunction here. Okay. If you see what? Two blocks right in the middle among three sum injunctions. Let's say if you move this guy to here. Let's say this is G1, this is G2. If you move G1 from the output side to the input of sum injunction 1, let's give them the name. Sum injunction 1. What's going to happen? What's going to happen? G1 is over here, right? That's 1 and that's 2 becomes what? Adjacent, right? Adjacent. Next to each other. Does that make sense? Does that make sense? Of course, you have to follow the after moving G1 over here, you need to do something else to the rest of the inputs of the S1. Of course, you're going to do those. Okay. I'm not excluding those. I'm just giving you an example to here. After this moving, you see what? These two next to each other. Very good. Very good. Guess what? You can combine them together. This becomes one single summing junction. Does it make sense? Because you are conducting plus or minus here with bunch of inputs, you are doing the same thing here. So these two can be combined. Does it make sense? You plus minus here, and then you minus plus here. Okay, I put them together. It won't affect any result. Does it make sense? It's equivalent. So after this, you can combine these two. These two summing junctions, now you can combine them together. It becomes one single summing junction. This is nothing but reducing the number of the summing junction. Does it make sense? So this is the idea. This is the idea. Okay. So how to move and where to move. Okay. You need to make a decision. And based on what? Based on this idea. Okay. After moving, you need to be able to combine the summing junctions or peak-off points. All right, if any questions before, once again, before the example? Any questions? All right, if this is clear, then let's do the example here. Go through some example, you will know what I mean by everything. What I mean by everything. First example, it takes a little time to sketch this given system, but you have no choice. Here we go. This is example one. If you roughly count it, you can see more than one, three summing junctions and four peak-off points. Okay. Obviously, we need to do something. We need to do something we need to move something to have a better look of the overall system. Okay. So this first example, let's do it together. Yeah, let's do it together. Let's do it together. Step one. Yeah, step one. Organize this and recalling the tips. Number one, we just mentioned. We need to look through the given system to see any available basic ones, right? Anyone see any basic ones? Cascade, parallel, or feedback? Anyone see any basic ones like those? Good. I see Alex and two Alex. Coincidence. Two Alex. Both of them are found the feedback. Feedback at the right end. Very good. Feedback at right end here. Here, let me explain a little bit. Okay. Probably some confusing or some bad feeling you might have about this input here from up here. But if you only have one input here, one feedback signal here, and then you feel very confident to consider this as a feedback system, no problem. However, you have another input here, up here. And how to understand this then? It's actually here equivalent to what? Equivalent to this, okay? This is G2. Equivalent to what? Equivalent to separate this top input and the rest of the feedback by doing this. We just mentioned the example how to combine two summing junctions. However, if you want to separate them, of course, they also valid. Does it make sense? This guy is nothing but this guy. Does it make sense? This guy is nothing but this guy here. Does it make sense? And of course, from here, you can see a clear feedback here. Better look than here, right? This is how you see it. This is really how you see it, actually. This is how you really see it. Okay. You separate this, or say split this summing junction into two. Of course, you can do it. Plus minus equals to plus and minus. Of course, right? Because of that, you can do combination between G3 and H3, right? So step one, what we do is combine G3 and H3. And then here, we're gonna write a note here. We know this is the feedback, right? This is actually feedback. And anything else? Any other basic ones? Any other basic ones we can see? Are there any? Correct. None. Okay. No more. No easy ones. No basic ones. No more. Okay. Basically, this part of the system, we need to do some moving. We do some moving. There's always one way to move. Okay. So how you move, actually, sometimes it doesn't matter which one to move. Either way works. Yeah, either way works out. It's just what matter is just some of movings are easier than the others, and then the others. So, any proposal here? Anyone you want to move from where to where?
Move G1 to in front of that first summing junction.
G1 to where?
R.
G1 to R. It's okay. It's doable. Now, why we are doing such moving?
combine the next two summing junctions together?
Yep, we can. After that moving, we can combine these two summing junctions. Good idea. Anyone has any other idea? Moving G1, yep, absolutely sounds reasonable. That's a good idea. Any other proposals?
Can't we convert the feedback loop to one of our transfer functions that we've already derived? Or no.
You were talking about this?
Yeah, like to just a one flat transfer function, or no? Is that not possible?
Absolutely. That's exactly what I mean by combine. What I mean by combine. Combine means this guy becomes one single block. We're not doing
we
yet.
did that? I thought we were.
No. We are not doing that yet because I just want to, at one step one here, do two things. But okay. Maybe since you don't want to do that, we can do this. We'll save here, and then we can have some injunction here, and then we got C. Yep, like we just said, we'll combine G3 and H3 together, and then what do we end up with here? What is it? There's a ratio, right? Numerator is whom?
So it should be G3 divided by 1, and then we're doing negative feedback, so it should, I believe, be positive HS, which is going to be H3 times G3.
There we go. Correct. Okay. This is the result of combining G3 and H3. And the rest of the block diagram, of course, remain. Right? And then we consider step 2 as the moving, as the first moving. Kevin proposed to move G1 from output end to the input end of the R. That's a good idea. Okay. Any other idea, actually? You can achieve combining the peak off point and or the summing junction. Any others? Yeah, Alex here proposed to move G2 to the left of the peak off point. Very good. Now guess what? This is actually same as my idea. Okay. Let's assume that this peak off point as number 1. Peak off point number 1. Okay. Alex proposed to move G2 from output end to input end of it, which is here. And this is my idea. It's not necessarily better than Kevin's idea. However, just follow my notes here. Okay, easier. So let's just follow this idea. Okay. So move G2 over 1 peak off point 1 to here, so that you can combine this peak off point number 1 and this peak off point. Does this make sense? Okay, this can also achieve that. So what we do is keeping R here, this summing junction, these things remains, G1 remains, summing junction remains, and then what? G2 now is here, right? And then what? Summing junction 1 here, combine was here, reach this summing junction, and reach this G3 over 1 plus G3H3 C. Right. Here, of course, be very careful. Be very careful. I'm using the red color to emphasize. Your G2 from output end move to the input end of the 1, right? And then according to the algorithm, if you go back to your notes, what's the algorithm? The other output of peak out point 1, which is here and only here, need to do what?
Put a 1 over G2.
Exactly, times 1 over G2. Here we go. Good. To reach the next summing junction. Be very clear in your mind. Be very, very clear in your mind. Okay. The rest of the thing remain same.
Can you move the paper for us, Dr. Zoe?
Oh, yeah. Take a look. Take a look to see any questions. Of course, here is H2 remains same. That makes sense. You move G2 from. Let me do here. You move G2 from the output end once again. Okay, be very clear which block and which peak out point. Okay, be very, very clear. G2 is output end of the peak out point 1. Okay, you are moving from output end to the input end of it. So, okay, it already happened. It's already happened. Now, 1 here is combined with this guy. No, okay, you can go ahead to combine. However, never forget there's another output of the peak out point 1. Need to divide it by the moved transfer function, which is G2. That's why you have this red part. Makes sense? But take a look to see if this move makes sense. So moving G2 from output to input of peak out point number 1. This is what we did. This is what we did. Any questions? All right, if this is clear, then what's the next? Anyone? Any proposal? What we should do next? Here, very good. Okay, very good. When you reach the next when you opt right after the moving, okay, successfully moving, you need to think of the tip number 1 again, which is look through the entire system now to see any available basic ones. Okay, this is very important. Okay, after 1 moving, okay, it's time to check the system once again to see any available basic ones. Rather than hurry up for the second move. Does it make sense? Don't rush to next move. Okay, not yet. Okay, go back to tip 1, check the system to see if any new available basic ones, so that you can do easy combination. Okay, remember that. Okay, remember that. So Wally is saying from this resulted system here, he is saying, well, clear what? A feedback between G2 and H2. Here. Right? And not only this, right? Anything else you can see as well? Anything else? 1 and the 1 over G2. Very good. Excellent. Here. Combine 1 unity and 1 over G2. Be very clear, okay? Be very careful as well. 1 and the 1 over G2 here. This is what? Which basic one? This is what? It's a parallel. Oh, very good. Okay, Wally is right. Be very careful. This is not feedback. These two are parallel. Okay? Be very, very careful. These are not feedback. These are parallel. Anything else? Anything else? Because actually after these two combinations, the things becomes very, very easy, isn't it? This becomes super easy now. This remains. G1 remains. The summing junction is gone, right? Summing junction is gone. Here you have a G2 over 1 plus G2. And then you're reaching pickup point number 1. And then you have 1 plus 1 over G2. And then don't forget the original feedback here. Right. And things now is much, much easier. Becomes much, much easier. Does it make sense? By here, basically, we all know how to do it, right? We all know how to do it. We all know how to do it. You can do. Once again, check, okay? And never forget the check. By this system, you check what? These two are what? These two. Yep, Alex, right. Cascade. Yeah, these two cascade. Now about these two. Same, right? You're seeing two cascades. It couldn't be easier. Couldn't be any easier. This becomes G1, G2, 1 plus G2, H2. Cascade is just a product. Okay. Cascade is just a product. And with a feedback of H1 here. Don't forget. And these cascades, you just need to do like this. Right? Pretty much you combine two cascades, and then this is out its a block diagram. Right? Okay. And then step 5, I think, is very straightforward now. Step 5 is very straightforward. And just the one feedback, and it's just the one feedback. And then what you need to do is, this is feedback, right? This is feedback, and then what you got is G1, G2, 1 plus G2, H2. Here is 1 plus what? G1, G2, H2. 1 plus G2, H2. Makes sense? This is the feedback result. Cascade with Rest one. Does it make sense? Any questions? The step is there's one feedback here. Step 6, last one cascade. Right. R times bit ratio here times 2 parentheses here. As the final result. Right. So take a look to see any questions you have. This is our first example. Any questions here?
How was it that that one line was 1 again? I think it was like step 3.
Oh, here.
Somewhere around there. Or
Here,
step,
right?
Yeah.
Everybody, look at here. When you have a signal here, and you go through and then reach output, there's no transfer function in the middle, right? But they're equivalent to this, right? Does it make sense now?
Okay. We can immediately assume straight line is just 1 for that. Okay.
Straight line means with a gain of unity. Absolutely not 0. Okay, absolutely not 0. What does it mean by 0? Which case is 0? Which case is equivalent to 0? Which case? Open circuit. Okay, open circuit. Okay. No matter what is your R, your C remain as 0. Nothing. You're not receiving anything. Open circuit here. Well, if you don't want to say open circuit because this is a diagram, a signal route. It's not a circuit connection. So we don't want to say open circuit, but there's nothing in the middle. This is 0 gain, which means no matter what is your input, your output is nothing. Always nothing. It doesn't matter. Input, no matter how you make efforts from input and your output is 0. Because gain is 0. Does that make sense?
Yeah. Thank you.
All right. Sure. So when you do the combination there, this step, and that's very important. Realizing this is one input, okay? This is with gain, with transfer function of unity, 1. And going in summing junction, okay? That's why you have 1 here as a forward transfer function. This is the another forward transfer function. These two are parallel. 1 plus 1 over G2. That's why. And what do you need to do? Obviously, go back home to redo this example by conducting different moving. For example, at the beginning, you use step 2 here. Don't follow me, but follow Kevin's idea to move G1. And then go ahead to see if you end up with the same answer here. Okay. All right, we still have 10 minutes or so. Anyone realize what we need to do today? We should really do today. Review, here we go. There we go. Very good, very good. Okay. Exam review. Exam review. Okay. here. Let me give you some. So exam time has been settled based on the exam time survey. Everybody agreed to the time, which is next Monday from 1 to 2:45. All right. Specifically, is 90 minutes for you to conduct the exam and plus 15 minutes to uploading the answer sheet. Okay, so and then what you're gonna see is first problem is the multiple choice. Okay. Multiple choice. You might have the total point is 15 points, so you either have 10 questions with 1.5 point per question, or you can have 15 questions with 1 point per question. Okay, is that clear? This is a multiple choice. I cover the modules we have learned so far. As you know, the midterm 1 covered module 1 through 3. Okay, module 1 through 3. Okay, 3 modules. I covered the basic concepts, especially. See you understand those. Okay, this is the multiple choice. Okay, in the quiz, you're gonna select over there. Problem 2 is here. I'm pretty much telling you the statement of the problem. It's gonna be, I believe it's gonna be exactly same. Okay, I believe it's gonna be exactly same. So a system is modeled by the differential equation, and assuming 0 initial condition, and then find the frequency domain transfer function. Well, this problem should be very easy. It should be very easy. Take you maybe 5 minutes, 5 or 6 minutes. Okay, don't overthinking of it. It's just a simply Laplace transform. We have done the very close example in the lecture. Okay, so go back to your notes. You should be able to find it. And of course, be very careful the definition of the input and output. Okay, this determining who is the numerator, who is the denominator. Right? Be very careful. And the next problem here is the problem 3. What is it? The other way around, right? The other way around, right? So given S domain function, capital letter F of S, and then applying inverse Laplace transform inverse Laplace transform, to find the corresponding time domain function, f of t. What this problem is about? Partial fraction, right? It's really nothing but partial fraction, right? We have example as well, right? Example as well. Like I said, the partial fraction could be very complicated, so I'm not planning to make it that way at all. So I just keep a moderate difficulty level for you to do. So the examples in the notes should be sufficient. Okay. Problem 3. Problem 4 is given the circuit. We have such kind of an example in the notes as well. Right? Given the circuit, first of all, you need to convert all of the components, RLC, into S domain function. What does it mean by S domain function? It means nothing but what? S domain impedance, right? RLC. What are the frequency domain impedance in terms of S? Excuse me. What are they? You should know. Based on those impedance, you're conducting what circuit analysis. It's not complicated circuit analysis, but you still need to conduct the circuit analysis so that you can find the transfer function. And here, I'm defining the output and the input again. Okay, so you need to find the corresponding two variables. Okay. This is the problem 4. The last problem is the block diagram reduction. Okay. By reduction is once again just like the example we just did. Okay, that's just even a complicated block diagram. You are trying to reduce it to one single block total transfer function result. Okay. Including the multiple choice, you have up to 5 problems. Okay, 5 problems. 90 minutes. And problem 2 should be very easy. And no more than 6 or 7 minutes. It shouldn't. Problem 3, a little bit more, but not too much either. Okay, partial fraction part. Problem 4 is the circuit analysis, a little bit circuit analysis. But here, this problem, be careful. If you are able to find out the ratio between 2 variables, that's good as the result. If you can't, the circuit and the impedance in frequency domain, those are much more important. Okay, the algebra calculation part, well, maybe I can give you 3 points over there. But the major points are going to be given to the circuit equations. Okay, equations. Okay, be given equations. It's all up to how much time you have. Okay, you have plenty of time. Okay, go ahead for the calculation. If not, okay, leave the calculation to the last. Okay, be very careful. Okay, know how to assign your time. Last problem is probably a little bit time consuming, so you just be prepared. Okay, it's a step-by-step procedure, and the final result is something just like this. You don't need to organize it. Okay, you don't need to. Okay, keep it this way. It's a better result than you make what. Make everything becomes like one polynomial like this, and the denominator another polynomial. No, it's not a nice result. This is. You see, parentheses. I mean, you need to populate it. What I'm saying is, 2 parentheses are these 2. Parentheses are these 2, and then times this guy. This is the best result. You don't need to do any further organization. Did I make myself clear? All right. Thank you, Sawyer. And these are the 5 problems. We got a no sheet. Yes. And no sheets allowed. Okay. So closed book, but 1 formula sheet allowed.
Are we allowed to print up the 2 Laplace transform equations, the theory and the Laplace transform?
And here it's saying 1 formula sheet and all of the handouts are allowed.
Oh, okay.
Actually, in your sheets, in your hands, you have about what? 3 sheets, right? One is formula sheet, and there are 2 transform Laplace and transform sheets. Yes, so you have 3, up to 3 pages. Okay. Any other concerns?
I have a non-exam related one.
Non-exam related. Okay, go ahead.
On the homework, that was due yesterday, right? Or today?
Today, at the end of today.
Okay. I couldn't figure out 17A because the book said a different answer than I kept getting, and Chake said a different answer than the book.
You couldn't get 17A. You mean the answer, or you couldn't get the problem?
I couldn't get the answer to match what the book's answer was.
Oh, 17A, right?
Yeah.
Of course, first of all, I'm gonna present the homework solution. That's for sure. After the due time. And second, Well, let me take a look at the problem first. Maybe it costs a little bit of time. Can you wait to see the solution, or
I can wait. I can wait. I didn't.
Yeah,
I didn't agree to courses.
yeah, you guys that have won't lose any points, okay, for the homework. You guys won't. A good exercise, that would be great, okay, but the homework solution is going to be provided. No worry.
Okay, thanks.
But if the homework makes no sense, or just like you said, you couldn't see how you got there, and then let me know. Let me provide more insights. Okay, let me know in that case. Okay, if homework solution is not satisfying, let me know.
Thank you.
Sure. Do we have a T0 turning? What do you mean, Lucas, by that? The homework. Yeah.
He meant
homework-
to say 2.
What is that? I'm not following at all.
He meant to ask if we.
What?
My question is, do we have to turn the homework in?
You don't have to. You don't have to. This is not required. It's not. Well, let me repeat. I thought I have made this very clear. However, probably not quite. Look at the syllabus. Okay, no one can violate the syllabus, which is the grade distribution here. There's no homework space. There's no space for homework. Okay? It's not counted towards the final grade. I can't make any otherwise happen. Okay, it's already in the middle of the semester. I can't change. Okay, I can't change. You don't have to, but some exercise are good, of course, helpful. So, any other questions? All right, so thank you for attending to this lecture, and my office hour obviously is right after, so you can reach me from the Teams. And other than that, talk to you guys on Wednesday. When we're gonna finalize the module 3 with more examples. Okay, thank you. Bye now.